Hi, my name is Edward Elliott. I'm a lecturer in the philosophy department at the University of Leeds. In this short series of video tutorials, I want to introduce to you some of the fundamental ideas and concepts of probability theory. In this video, I'm going to be discussing probability distributions. But before we can get to that, if you haven't yet seen the first video in this series, then I strongly recommend that you watch that one first. In that earlier video, I went over the concept of an outcome space, and in the present video, I'll be using the same example as I used back then. So a lot of what I'm going to say isn't going to make much sense if you haven't watched the first video. Now you'll recall that, according to the example that I used then, that you are to imagine that you're at the zoo and you've lost your map and all the signs are missing for what's at the next exhibit. In this case, we were going to conceive the outcome space as a set of points where each and every single one of those points represented a different kind of animal. And since we assumed that you were primarily interested in both how dangerous the animals are and how cuddly they are, we ordered those points along two dimensions, these two, in order to better reflect that which you care about. So now that we've got our outcome space, let's talk about probability distributions. The outcome space represents all the various different outcomes that might turn out to be true when you eventually reach the next exhibit. But notice that, while it's true that you don't know for certain what kind of animal you're going to see next, or indeed where in the general area of the outcome space it's going to end up, it could still very well be the case that those different outcomes under consideration might have different probabilities. Some of them, for example, might be more or less probable than others. And this is a difference which we've not yet represented in the outcome space, because in that representation all of the outcomes are being treated as if they're equal. So in order to represent this extra information, we're going to need something extra. And that's where the probability distribution comes in handy. This is something that's going to allow us to represent the different degrees of probability that attach to all of the different outcomes. Now, generally speaking, a probability distribution is a function that tells you the probability of each and every outcome there in the outcome space. For example, a probability distribution might say that there is a 1% probability, or equivalently a probability of 0.01, that the animal that you see in the next exhibit will end up being a rabbit. And it might also tell you, for example, that there is a 0.03 probability that it will be a zebra. It will continue and do this for each and every single one of those specific outcomes. In this case, we could write that down as the probability of rabbit equals 0.01, and the probability of zebra equals 0.03. And thus it continues until the probability function has assigned a value for each and every single one of those specific outcomes. But the function is also going to assign probabilities to those non-specific outcomes that are there in the outcome space as well. For example, the function might say that there is a 0.4 probability, or a probability of 40%, that the animal will be dangerous, and a 0.2 probability, perhaps, that it will be cuddly. Again, we could write this down as the probability of dangerous equals 0.4, and the probability of cuddly equals 0.2. We keep on doing this until a specific degree of probability has been assigned to each and every outcome. However, there's a catch. A probability distribution cannot just assign probabilities to outcomes in any old way. There are rules that any good distribution has to satisfy, and these rules are critically important for understanding what probabilities are. For example, if a probability distribution says that it is 0.4 probable that the animal will be dangerous, then it cannot also say that the probability that the animal will be both cuddly and dangerous is, suppose, 1 or 100%. You should see that this makes no sense. If it is 100% probable that the animal will be both dangerous and cuddly, then it should be 100% probable that the animal will be dangerous, since being dangerous and cuddly obviously implies being dangerous by itself. Or let's consider a different example. Imagine that the probability distribution says that it is 0.4 probable that the animal will be cuddly, and it also says that it will be 0.4 probable that the animal will not be cuddly. Again, this should make no sense. Where did the other 0.2 go? So these examples suggest that a probability distribution has to be well behaved. Or, to put that in slightly more technical terms, a probability distribution has to satisfy certain axioms. Luckily for us, the axioms are actually very simple, and there's only 3 of them. The first axiom is probably the easiest. It says that the probability of any outcome has to be no less than 0. That is, there cannot be any so-called negative probabilities. The second axiom is almost as easy as this. It says that the probability of the trivial or the necessary outcome has to be equal to 1. Or to put that in slightly different terms, if some outcome is necessarily true, if it is guaranteed to be true no matter what happens, then its probability is 100%. And then finally, and this axiom is a little bit more difficult, if any 2 outcomes are inconsistent with one another, and recall that means that they cannot both be true at the same time, then the probability that at least one of those outcomes will be true must be equal to the sum of their probabilities individually. Now this is the hardest one to understand, but fortunately there is a relatively easy way to visualize what these 3 axioms say when they're put together. And that is, metaphorically, that any probability distribution has to be like a distribution of mud. Let me explain what I mean by that. Imagine to begin with that the outcome space is the surface of a table, and then imagine the probability distribution as some quantity of nice thick mud that has been spread out or distributed over the table, just like this. Now the total amount of mud can be anything that you like, but for simplicity, let's suppose that it's exactly 1 liter. Now to work out the probability of any outcome, all you have to do is count up the amount of mud that is situated directly over the part of the table that corresponds to that outcome. So in the example given here, the probabilities are centered evenly around the middle of the outcome space, and this represents that it is probably going to be the case that the animal that you see next is not going to be particularly cuddly or particularly not cuddly, nor is it going to be extremely safe or extremely dangerous. It's going to be situated somewhere in the middle of that outcome space. In other words, the distribution is telling you that the most probable outcomes are those towards the center of the outcome space. But it also represents the probabilities of individual outcomes. So suppose you wanted to know specifically the probability that the animal will be, let's say, not cuddly. This outcome, if you'll recall, is represented by that area on the bottom half of the table. And in this case, about 50% of the mud is situated over that half. So the probability function is telling you here that it's only 50% probable that the animal will be not cuddly. Likewise, suppose you wanted to know the probability that the animal will be both not cuddly and dangerous. This outcome is represented by the area on the bottom right-hand corner of the table, and only about 5% of the mud is over that corner. So again, the distribution in this case represents that it is 5% probable, or 0.05, that the animal will be both not cuddly and dangerous. So given that, let's now go back to those 3 axioms that we looked at before. The first axiom said that the probability of any outcome is not less than 0. So let's think about this in terms of distributions of mud. And if you do this, then it should make sense. No matter how you distribute the mud over the space of possible outcomes, the amount of mud that's above any given outcome must always be either 0 or more than 0. It's not possible to have a negative percentage of the mud above any outcome, so it is not possible to have any outcome with less than 0% probability. And since that's true for every single possible way that you might distribute the mud over the table, therefore it must be true for every probability distribution. The second axiom said that the probability of the trivial outcome, or the necessary outcome, must always be 100%. Again, this is very easy to visualize once you see probability distributions as if they are just distributions of mud. After all, remember that the necessary outcome corresponds to the entire space or the entire surface of the table. So, it doesn't matter how you try to distribute that mud over that space, it's always going to be true that 100% of the mud is over the entire thing. And since that's necessarily true for every way of distributing mud over the table, therefore it will also necessarily be true for every single probability distribution. The final axiom, as we've seen, is the trickiest. It says that if any two outcomes are inconsistent, then the probability that one or the other will be true is going to be equal to the sum of their individual probabilities. So let's break that down into its parts. First, recall from the first video that when we say that any two outcomes are inconsistent, what we mean is that it's impossible for them to be both true at the same time, and in terms of the outcome space, that means that they do not overlap. An example of this would be the outcome cuddly, and the other, somewhat more specific outcome, not cuddly and dangerous. These cannot both be true at the same time, so they're inconsistent. So what is the probability that either the animal will be cuddly, or it will be not cuddly and dangerous? Well, as the axiom says, that outcome is just the sum of their probabilities. So to work it out, all we have to do is add up the probabilities of its two parts. So, since about 50% of the mud is above the outcome cuddly, and only about 5% of the mud is over the outcome not cuddly and dangerous, therefore 55% of the mud is going to be over that larger outcome, either cuddly or not cuddly and dangerous. So now with those points established, let's just consider some interesting and important consequences of those three axioms. The first important consequence is that if one outcome A entails another outcome B, then the probability of A cannot possibly be more than the probability of B. This you can easily see if you represent it in terms of mud. If one outcome A entails another outcome B, then it must be the case that the outcome A is contained inside of the outcome B. And since A is already included inside of B, it must be the case that however much mud is over it, there cannot be any more mud over A than there is over B. A second interesting consequence is that the impossible outcome always has a probability of 0. You can think of the impossible outcome as just the opposite of the necessary outcome. So, while the necessary outcome takes up the entire 100% of the table, the impossible outcome is going to take up exactly 0% of the table. And because it doesn't take up any of the table at all, it can't be the case that any of the mud is situated above it, and therefore it has a probability of 0. The final interesting consequence that we will consider: for any outcome A, it's always going to be the case that the probability of A is equal to 1 minus the probability of not A. So to visualize this, first notice that any time that you have one outcome A, the other outcome not A is just going to be that part of the table which is not the A part. Given this, if you've got, let's say, 20% of the mud over the A part of the table, it must therefore be the case that 80% of the mud is over the rest of the table, which of course represents the outcome not A. So that's just 3 interesting consequences, but it is worth noting that literally anything which is true about a probability function you can represent also in terms of distributions of mud. In mathematical terms, these two things are isomorphic to one another. So that concludes our discussion of the mathematics of probability theory. In the next video, we're going to talk instead about the philosophy of probability, and we'll consider what these different probability functions that we've been looking at could possibly represent.